In this, we are going to learn another method to solve differential equations, what we call the convolution product method. Remember, we had a situation where uh, we want to have a result for this one. For example, what is the Laplace transform of the product ft gt? So we kind of expected that this um, may be equals to Laplace transform of ft times the Laplace transform of gt, but unfortunately that is not the case. They are not equal. So you cannot write a product of um, Laplace transform product equal a product of Laplace transforms. That doesn't work. Okay, so not true. So uh, so this is it's important. Okay, so we're going to say important because we kind of write it by mistake like that, but that's not true. Okay, so they are not equal. So instead we have a result what we call the convolution product. So let's talk about the convolution product first. So what we mean by that? So let's go with the definition. So the definition, the convolution product. Sometimes we just say convolution. So we can say convolution product or simply convolution. So how we define it? So let's say so let f and g be defined let's say for t positive, okay, or 0. So then the convolution product, the convolution product, then the convolution of, let's say, ft and gt is defined by, so is the convolution of ft and gt is defined by, so that's a special notation. We use star for that. So we use f star g. That means the convolution. Okay, so that's just as one function. So that's just one function of t. So how we define it? It is from 0 to t, 0 to t. If we use another Greek letter tau, so if tau g t minus tau. So we subtract. So we write tau and then t minus tau. Remember the format, t minus tau and then d tau. So that is the convolution product. And then you can see that it doesn't really matter which one we're gonna use. So we get the exact same answer even if we switch the two terms. So if t minus tau times g tau. So tau is the dummy variable in this case. So interestingly, you get the same answer in both cases. So that's the definition. So pick whatever you like. So what we normally do, we're gonna put t minus tau to the easy one. So we're gonna put t minus tau to the easy one. You can see the t minus tau term. So you put it there for the easy one so that it's easy to integrate. So we can leave the difficult one. We just put tau for that. So that's a formula. That's the definition. So let's try to do some examples just to see how these things gonna work. So you can see that they are the same. Okay, you get the same answer. Okay, you get the same answer, and then you can prove that they are the same. But we are not gonna do that. But just for information, remember they are the same. So let's try to look at maybe some special examples. So let's do this one first. So example. So let's say if t equal e to the t and gt equal t for t greater than or equals 0, find f star g and g star f, just to see whether they are the same. Okay, at least one example. So let's start with the first one. So f star g, by the definition, it is 0 to t e to the tau. Then, so what are the two functions? One is e to the t, the other function is t. So let's put the t minus tau for the second one. Okay, so t minus tau d tau. So that's the definition. Okay, so this is the definition. Okay, that's the definition, one definition. So let's continue. So this is just a integration by parts problem. So we can continue this one. So you can use either method, whether the DI method or the other one. So if you do that, so I'm going to use for this one just a regular method. So what's a regular method? We normally pick this one as U. So that's a kind of tradition. And the other one is dv. So let's do that. So we have u and dv. So u equal t minus tau, u equal t minus tau. So it is t minus tau. Yeah. So let's write it like that. So u equal t minus tau, dv equal e tau d tau. Remember, the tau is a variable, so the t is a constant now. So that means what will happen? Du simply become minus d tau. V is e tau. So we have all the 4 ingredients. So we're gonna plug in here. So if you plug in here, what's gonna happen? So you're gonna get uv. Okay, so uv means t minus tau, that's u. P means e tau, and then evaluate at t and 0, and then minus we have a vdu, so 0 to tau. V means e tau, and du become d tau, but with a negative sign become positive. Okay, so that's what you get. Now let's plug in the values. So when you plug in t, so this become t minus tau become, because we plug in the t for the tau, because tau is a variable, so this becomes 0. And then when you plug in 0, so what will happen is a minus. When you plug in 0, you're gonna get t, and then e to the 0. So that's what you get from the first term. So you have tau equals 0, and then so you get that, and then plus the other one is easy to integrate, e to the tau, so and t 0 and t. So you're gonna get from the first one, from the second one you're gonna get e to the t. I put that first, and then you get a negative t here, and then minus 1 here. So that's the answer if you use the first product. So let's use the second product. So I'm gonna kind of switch the terms. I can show you what happened. So I wrote this term first, and then that term second, just to get like a nice expression at the end. Okay, so good. Now let's try to do the other way and see whether you get the same answer. You should, but see whether you get the same answer. So just an experimental thing. So now if you do the other way, so what's gonna happen? F star g again t So we know that we can even so we can switch, so we can put the t minus tau to the other one. So let's do that. T minus tau goes here now, and then tau d tau. So what we did, you have option to put tau in one function, t minus tau in the other function. So normally what we do is we're gonna put t minus tau to the easy one. Okay, but let's see how we can simplify this one. Here something interesting happened. You know that e to the t is a constant because the tau is a dummy variable. So that means e to the tau you can take it out from the integral. So that's gonna make it a little simple. So we can take e to the t out of the integral. So you have e to the t, e to the negative tau, and tau d tau. That's what you get. So now this looks simple actually compared to the previous one, and we can do the same thing as before. So the answer is e to the tau. So let's try to write the integral now. Again, it's the integration of past problem. Now I'm going to use the di method for this one, just to show, remember what we did. So d and I. So normally for the derivative part, we're going to pick normally the easy one. So it is t, because once you take the derivative, it's going to make it simple, and then e to the minus tau for the other one. So if you do that, they're going to get 1. And then here it's going to get minus e minus tau and 0. And then you're going to get another minus sign, so you get e to the minus tau. That's what you get. And then what we do normally is you're going to multiply like that, multiply like this. This is 0, so you're done. Plus, minus. Good. So you have the answers now. So let's put everything here. So what's going to happen is you're going to multiply that price and negative. So we have tau e to the minus tau, and then another negative, and e to the minus tau, and then what we're going to do, we're going to put the numbers there. So what are the numbers? T and 0. Since it's just one expression, you can do that, but be careful, sometimes you get an integral. Good. So let's plug in the values now. So we have e to the t. Let's plug in the t first. So if you plug in the t, you're going to get negative t, e to the negative t, negative e to the negative t. That's what you get in the first one. Minus, now you plug in 0. Once you plug in 0, the tau, because the 0 is gone, and with the negative sign it becomes plus e to the 0, so which is 1. So that means if you simplify, you're gonna get, you can see here when you multiply these two, the e to the negative t get cancelled, and from the last term you're gonna get e to the t. So you get e to the t because if you multiply the first one with the last one, you get e to the t. And then from in the first term you get minus t, and then from the middle term you get minus 1. So you can see that you end up getting the same answer. But the benefit here is this looks simple. Okay, so that's what happened. So you can see that they are exactly the same. So it does not really matter which one, but sometimes when you have exponential function, this is little easier compared to, because you can pull out the e to the t term. So once you pull out e to the t term, you have a little easier integral, and then after you get the integral, you can use the di method or the regular method to, it's just an integration by parts problem, but and how we do it, so it's up to you whether you want to use a regular technique or the di. So somehow, so this is what you get, and then you plug in the numbers and get the answer, so you get that. Okay, let's do one more example because this is a kind of interesting one, and we kind of need to know what's out there. So let's do one more example. Now let's try to find G star F. So what is G star F? So if you write G star F T, so it is 0 to T. So let's go with the two functions. So we have e to the tau and tau. So that means if you put e to the tau here, that's the first function. Actually, it's a g function. So what's the g function? G is t. So what will happen is going to switch the order. That's the only thing different. So that means actually, yeah. So we have t and e to the t. So that means it's the same two functions. So so we have t now. So it is. So I'm gonna put t minus tau for that one. So if I put t minus tau for that one, so you're gonna get that, and then the next one is e to the tau d tau, and you can switch the two. So once you switch the order, so we have 0 to t e to the tau t minus tau, and you can see that this is exactly the same as f star g in the first version. So this is kind of surprising result. So that means g star f exactly equal to f star g. So the convolution product becomes commutative. Okay, so what we call commutative. So that means you can switch the order. So a times b equal b times c. That's what we call commutative. We can talk about this later. So there are some results like that. So let's do one more example. So the next example is this. So let's say we have if ft equal sine omega t and gt equal cosine omega t. So let's try to find the product, because we know that f star g equals g star, so we only need to find one of them. So let's try the definition. F star g, which is equals to, by the definition, 0 to t. We're going to put to one of them tau, to the other one t minus tau. So I'm going to write so sine. So let's put tau here, so it's omega tau times the cosine for this one. Let's put t minus tau. Okay, so again, it doesn't matter which one, d tau. So that's what we get. Now the question is how to integrate this one. To integrate this one, we have to use one of the trigonometric identity. So let's write it. This we have the product rule. So we know that sine a cosine b equal 1/2 sine a plus b, and then we have plus sine a minus. That is one of the trigonometric identity. You can find them in one of the video. I put like all the trigonometric identities there, so you can find it there. Now what we can do is we can write the definition now using this identity. So what we want to do is we're going to pick what is a and what is b. So we can call this function is a and that function is b. So remember, it's omega t minus omega t minus omega t minus omega tau. So I mean, when you add the two, omega tau get cancelled, you only get omega t. So it's going to make it simple. And then we subtract from the first one the second one. So then what will happen? It's become 2 omega tau minus omega tau. So that's what happened. So that means your answer now gonna be f star g t is simply become 0 to t 1/2. We can write outside if you want, and then we're gonna add the two. When you add the two, you can see omega t get cancelled, so you get sine omega tau get cancelled, plus, and then we have sine. When you subtract, the first one get double, so 2 omega tau minus omega t d tau. So that's what we get. So this is very easy to integrate. So if you integrate this one, so what do you get when you integrate this one? So let's write that. I'm already here just to make it easy to compare. So this omega is a constant, so that what will happen is so in the first one, this is omega t, because you are integrating with respect to tau. That means omega t is a constant. So it's just sine omega t is just a whole constant. You just need to multiply by tau. So that means this is simply going to be 1/2 tau sine omega t, and then you're going to put t and 0 for tau, minus the second one. So what's going to happen to the second one? So here omega t is a constant, so you can just use the u sub, or this is actually very simple, because if you want to use, just use the u sub for this one. But I'm going to tell you a trick to do it, because omega t is a constant. So that means you only need to worry about 2 omega tau. When you do 2 omega tau, 2 omega is a constant. So we know that when you do when you integrate sine and cosine, what will happen is you're going to divide by that 2 omega. That's going to happen because sine, so it's a negative cosine term. So you divide by 2 omega, but we have a 1/2 outside. Because of the 1/2, you see that there's a 1/2 here. So that means you simply getting 1/4 omega. So 2 omega with 1/2, and then it's a cosine. So what will happen? 2 omega tau minus omega tau. So that's what happened. And again, the limits are t and 0. And once you plug in the two numbers, it simplifies very well. So you should get, I'm going to write the answer for that, what you get. So you can plug in the values and simplify. And once you plug in the values and simplify, you will get this one. So it's a good idea to see whether you get that. So you should get f star g tau equals to 1/2 t 1/2 t sine omega t. And we can use this later. We need this result for one of the problems. Okay, so that's about that. And you can see that that's not that difficult, but there are certain things that you need to remember. For example, for this one, we use the trigonometric identity. So let's talk about some of the properties that we have. So properties. So we need to talk about 3 properties. So the first one is the commutative. We know that f star g is equal to g star f. So this is what we call the commutative. So commutative. And then also we have this. So if we have a constant times f and then star with g, this is exactly equal to f convolution cg. So you can see you can switch the c, and also is exactly to c times then f star g. So you can do that. So you can see you can switch c with you can put c to f or g or to the whole product. So this is one of the distributive property. Another distributive property. And also we have the associative property number 3. So that means if we have 3 f star g star h. So here you can see that you did the first two and then the second one, third one, or you still get the same as if you do the first one times you do g star h first. So you do g star h first and then f. So they are all the same. So that's the what we call the associative property. So we have those 3 properties, and this is going to make all those calculations much easier. So then we have the most important result of this. So I'm going to write this as a theorem. So this is a very important result. So let ft and gt be of exponential order. Be of exponential order. We know that we need that to have Laplace transform exponential order. Then what's going to happen? Then the Laplace transform of the convolution product f star g function. If you try to take the Laplace transform of the convolution product, what's going to happen? It is the Laplace transform of the integral 0 to t f tau g g t minus tau, it doesn't matter which one. So what the result says, this simply gonna be the the Laplace transform of f times just the basic product times the Laplace transform of g function, just the simple product, okay? Just the product. So this is a major result. So what it says that if you try to take the Laplace transform of the convolution product, you simply get the product of the Laplace transform. So this is very, very important, and the benefit is when you try to find the inverse Laplace transform, that means we have this result. So inverse Laplace transform of a product of a Laplace transform is simply the convolution product. That means if you have a product, if you identify something as a product of Laplace transform, so what you can do is it's going to be simply the convolution product. So that is the one we actually trying to use. So this is the useful one when you try to find the inverse. So this is another way to find the inverse of a Laplace transform. So if you see a product, see the answer is simply the convolution. Simply the convolution. So what you want to do is you just need to evaluate the convolution product, and then you're going to get the answer. So what we can do is we can do like several examples to see how it works. So let's try to first example. I'm going to do maybe 2-3 examples for that. So let's do that now. So again, so this is the major result. So what it says that the inverse of a product of Laplace transform is simply the convolution of the two functions. Okay, good. So let's try to see some examples. So as the first example, let's do this one. So the example, find the L inverse of 1 over s squared plus 1. So you can see that we can do these kind of problems using just the partial fraction method, and then you get the partial fractions, and then you're going to invert. So that's one way to do it. We already know how to do that. So let's try to do the new way. So what's the new way? We try to identify this as a product. So you can see what we have is, so inside you're going to see this. So it's L inverse. You can see there are two functions. We have s squared times 1 over s squared plus 1. Those two are very familiar. So so we can say note that L inverse 1 over s squared is t, that we know, and L inverse 1 over s squared plus 1 is sine t. So we know those two functions. So that means according to the argument, what's going to happen is you just need to find the convolution, because it's a product. Okay, so that means, so thus what we can do, L inverse 1 over s squared plus 1 is equals to the convolution product of the two functions. So that means what we can do, we can use the definition of the convolution. So we already know the functions t and sine t. So that means this is simply t star sine t. So you can write the answer like that. That's the answer. But normally what we do, we're going to simplify. Don't just leave it like that. Just try to find it. But that's the answer in convolutions. So we can use the definition now, this 0 to t. So you can put to one of them the t function. We know we have sine, so we try to leave it like that. So that means we try to put t minus tau for that, and then this is simply sine tau d tau. So this is going to make it easy. Now what we can do is we can simply use the partial fraction method for that, not the partial fraction, integration by parts for that, and then we can simply write it. So what you're gonna get is you can use the di or the regular method. So if you use a regular method, that's the u that we're gonna pick. Because once you take the derivative, it's gonna look simple. So let's put it here. So we're gonna say u equal t minus tau dv equal sine tau d tau. So what will happen if you take the derivative, du equal as before negative d tau, and then v is simply negative cosine tau. Okay, so we have everything we need. So let's plug in here. So we have the UV product, so that is negative t minus tau cosine tau evaluated at t and 0, and then the next one is minus u minus vdu minus vdu, and you can see that there are two minus sign here, and with the minus sign, the formula, you end up with a minus sign. It's a minus vdu, that means 0 to t cosine tau d tau, and then what you can do, you can plug in the values and simplify the integral. Once you do that, you end up getting t minus sine t, and you can see that that's exactly what you get even if you use the partial fraction method. This is one of the examples we did under partial fraction method, and you end up getting the same answer. So this is how you use the convolution product to find the inverse Laplace transforms. So let's do one more example. So as the next example, we can do this one. For example, find L inverse of 1 over s squared s plus 1. So we can do this in two different ways. So first, let's try to kind of recall what we did using the partial fraction method. So what we're trying to do is we can write the partial fractions first. So it is s squared s plus 1, which is identical to a over s plus b over s squared plus c over s plus 1. And then we're going to multiply, so you can have 1 identical to a times s, and then we have, actually that's not right, so we have a, we have a times 1s is missing and s plus 1, and then for b we can see only s plus 1 is missing, and then for c you can see s squared is missing. So that's what we have. We normally use a substitution first before you go for the coefficients. So we're going to go with the substitute. We're going to go with s equals 0. Once you plug in s equals 0, you're going to get 1 equal b, in other words b equal 1, and then we're going to go with the substitution s equal negative 1. Then you're going to 1 equal, if you put negative 1, you're going to get c, so c times negative 1 squared. So this says that c equal 1, and then so we're done with the substitution. Then we use the coefficient. So remember this trick because it's much easier if we do this way. S squared, that's the largest term. We normally go with the largest term. There are no s squared term here, and you get a squared when you multiply these two, and here those are the only s squared terms. So that means you can write 0 equal a, the coefficients are a and c. So this says that a has to be negative c or negative 1. So we have all three, and that's it. Now what we're gonna, so we have the inverse of that. So we have the we have the partial fraction for that. So we have I squared s plus 1 equals to a equal negative 1, so it is negative 1 over s, and then we have b equal 1, so s squared, okay, s squared, and then c is also 1, so 1 over s plus 1. Those are the three that we get. So now what we're gonna do is we're gonna find the inverse. So that means L inverse is, so we're gonna go term by term. So this is equals to so in a term by term, negative L inverse. I'm writing all of them just to recall what we did, at least just one example like that. And then we have 1 over s squared, and then we have L inverse 1 over s plus 1. So go term by term. I'm going to write the last one first, just to have like a nice pattern here. So we know that s plus 1, that means the each function is minus t, that's what you get from the last one. And the middle one says t, and the first one says minus 1. So that's what you get. Okay, so that's the inverse Laplace transform. Now let's see how the convolution product works for this problem. So let's do the convolution product. So that's the second method. So we're going to say method 2. Method 2 are the convolution. So when you do convolution, you don't need partial fractions. Okay. So so what was the argument when you do the convolution? We know that the if we have Laplace transform, the convolution, it is simply the product of the Laplace transform. Just a simple regular product, just multiply the two. Okay, so that means we want to identify a product, then we can go backward. So you can see in our problem what we have is s squared s plus 1, that's we have. So you can see this is simply 1 over s squared times 1 over s plus 1. So what you're trying to do is you can identify the two functions. So what are the two functions? So this one is t, this one is e to the negative t. So you identify the two functions. So that means this is simply the product between fs and gs. Okay, so we know that. And then in this case, the two functions are ft, which is t, and gt, which is e to the negative t. So we identify the two functions. What you want to do is just go with the convolution product. So according to the argument, the result L inverse 1 over s squared s plus 1 is equals to L inverse of fs gs, which is simply f star g according to theory. So let's do that. So it doesn't matter which one we pick, but we normally pick the, remember, or the easy one, we put t minus tau. So this is one of the example actually we did before. So this is again 0 to t. So we're going to pick the t. So it's a t minus tau e to the negative tau d tau. So we already did this problem and we already know the answer, so I can skip some of the steps. So the partial integration by parts gonna give you like this. So it's gonna be t minus tau e to the minus tau. So t0 minus 0 to t e to the minus tau d tau, and then you plug in the values. So you're gonna get t here. And then for the other one, you're going to get e to the negative tau t0. And if you put the answers, so you're going to get t plus e to the minus t minus 1. So you can see that does exactly match with the answer here. What we use is integration by parts. So no partial fraction. Okay. So what we did was this is another way to find the inverse Laplace transforms. So interesting. So what we can do is we can do just maybe one more example just to see how they work, and then yeah, so we did this one. So I'm going to do just one more example just to see the steps. Okay. So let's do this problem. So the example, find the inverse of, let's say, 1 over s times s squared plus 4 square plus 4. The same thing, what we try to do is we try to first identify the two functions. So you can see that 1 over s, no, we have s squared plus 4, which is simply 1 over s times 1 over s squared plus 4. And then you can see that the two functions are one, this one is 1, this one is 1/2 sine 2t. Okay, that means we identify the two functions, so we can use the inverse product now. So L inverse is simply 1 over s squared plus 4, which is I'm writing everything just to be logical here. So s squared plus 4, and then by the inverse property of the convolution, it is simply 1 convolute with 1/2 sine 2t. Actually, when you have a constant, it's gonna make the calculation much simpler, because what you can do is you can put the t minus tau to the constant function. That means it doesn't do anything. So that's what we're trying to do. So by the definition of the convolution 0 to t, we have 1. So that's the function we put the t minus tau. So you don't see that there. So that's where you put the t minus tau. And for the other one, you put the tau. So that means the next one is 1/2 sine 2 tau, 3 tau. That's what you get. So you can see this is a very simple integral. Then you have divided by 1 extra, so it's become a negative 1/4 cosine 2 tau, go with 0, t and 0. So once you plug in the two numbers, once you plug in 0, it's get negative 1/4, and then when you plug in t, is just cosine 2t. So that means your answer is going to be 1/4 minus 1/4 cosine 2t. You can see that this is much simpler than the partial fraction method for this one. So sometimes it's much easier. So it depends. Okay, so that's about that. And then you can see more examples in a separate video that you can find the description, where I only have the inverse Laplace transform techniques using the convolution. So you can see a few more examples there. Okay, so now let's try to move on to how to solve differential equations. So we're gonna do this one now. So let's say we have this differential equation. Good. So let's do this problem. So let's say solve the IVP, the initial value problem, x prime minus 3x equal 4e negative 2t along with x0 equals 0. So that's the problem we're trying to do. So what we do is we take the Laplace transform. So taking Laplace transform, we have sx minus small x0 minus 3sx xs equal. So we have to take the Laplace transform of that function. So that's the eat function. And if you recall, what is that? Le minus at is simply 1 over s plus a. So we can use that now. So that means this is simply going to be 4. Switch the sign. So it is s plus 2. And on this side, what we have, we know that the s0 equals 0. So that means this term is gone. So we have s minus 3 times sx equal 4 over s plus 2. So that means sx is equals to 4 over s minus 3 times s plus 2. So this you can identify as 4. I just put 4 to one function, it doesn't matter, times 1 over s plus 2. So what are the two functions? This you can identify with 4e3t, and this one you can identify with e to the negative 2t. So now what we need to do is just find the inverse. So we can do using the convolution method now. So that means xt is simply the L inverse of 4 over s minus 3 s plus 2, and this is a product of two Laplace transform. That means by the result, this is simply going to be 4. No, this is simply going to be 4 e to the 3t convolute with e to the negative 2t. So that's the result. Now what we do is we're going to find the convolution. So let's do that. So that means this is simply by the definition 0 to t 4e. So we can put the t minus tau to one function. I'm going to put that to the first function. It doesn't really matter. And then times e to the negative 2 tau d tau. And this is actually very simple. So you can see I can pull out 4e3t because those does not depend on tau. So 0 to t. What you left with is e to the negative 3 tau times e to the negative 2 tau d tau. So that means you can combine them. Once you combine, we have 4e3t 0 to t e to the negative 5 tau d tau. This is a very simple integral. Very simple integral. We know that we need simply divide by the constant. In this case, constant negative 5. So that means what you get is 4e3t. We have negative 1/5. Let's write it the other way. So it is 1 over negative 5 e to the negative 5 tau. We have t0. So let's plug in the values. So you're going to get negative 4/5 e to the 3t. We plug in the values. So when you plug in t, so you're going to get e to the negative 5t. And then when you plug in 0, you get minus 1. And when you simplify through, so you're going to get, what do you get? If you multiply the first two, 3t negative 5t negative 2t by some negative sign, I write the positive one first. So that means you're going to get 4/5 e to the 3t minus 4/5 e to the negative 2t. So that is the final answer. So that's the whole problem, and you can see that that's not that long. So we use the convolution product to find the inverse. So let's do another problem, maybe a little tricky. So how about this one? So let's do this one. So we have, let's say, solve the initial value problem. So let's say x double prime t plus xt equal sine 2t along with x0 equal 0 and x prime 0 equal negative 2/3. Yeah, so the answer, what you do, taking Laplace transform, we have x double prime xs minus s x0 minus x prime 0 plus xs equal, this is sine, so sine means 2 over s squared plus 2 squared means 4. Now let's plug in what we have. X0 equals 0, so that means this term is gone, so this is simply negative 2/3. So we end up getting s squared plus 1 sx plus 2/3 positive equal 2 over s squared plus 4. Now what we can do is we can move the terms around and divide. So we have sx which is 2 over s squared plus 1 s squared plus 4 minus 2/3 s squared plus 1. And then for the first product we can use the convolution. So note that 2 over s squared plus 1 times s squared plus 4 equal 1 over s squared plus 1 times, I put the 2 to the other one because it simplifies well, so like that. And then you can see that this is the fs function, this is the gs function, and because of that you can see the ft is simply sine t, gt is simply sine 2t. So that means if you take the inverse, is simply going to be the convolution of those two functions. So that means the L inverse of that expression, x squared plus 1 and s squared plus 4, is going to be the f star g. So that means actually we can write it like this. I'm going to write it is sine t star sine 2t, which is by the definition 0 to t sine 2t and then sine t minus tau d tau. So we put the t minus tau to the easy one, okay, and you can always switch the order because it doesn't matter. So now what we do, we use some trigonometric results to solve this one. We're going to call this is A and this is B. Then we're going to use the product rule, sine product rule. So let's do that. So if you use the sine product rule, so what's the sine product rule? So this is a sine product rule, so we can use that. So we know that sine A sine B is equals to 1/2 cosine A minus B minus cosine A plus B. This is not actually that difficult to prove. What we normally do is we write the cosine A plus B and cosine A minus B and add the two. Once you add the two, actually subtract the two because you need the sine. So subtract the two and then you're going to get the expression. So that's how you do it, but this is a trigonometric identity that we can use. So that means because of that, we have 0 to t sine 2 tau sine t minus tau d tau. So this is equals to, so what we do is we're going to take this as a and this part as b, so we can just plug in there. So once you do that, you get 1/2 the integral 0 to t. So what we get, you get a minus b. So if you subtract a and b, what will happen, you get 3 tau minus t. That's what you get from the first one, and then minus cos from the second one. What you do, a plus b, you add the two. Once you add the two, one of the tau get cancels, you get t plus tau. So that's what you get, and then you can see that these are very easy to integrate because t act as a constant. So that means the first one simply going to be 1/6 sine with a cosine sine 3 tau minus tau t0 minus and then here 1/2 coming outside, and then this again sine t plus tau, we put t and 0. Okay, and then we put those numbers and simplify. So what happened when you plug in t? When you plug in t, it's going to be 1/6 sine 2t minus 1/6 sine minus t, and from the second one you get 1/2 sine 2t plus 1/2 sine t. And then you can see that sine is an odd function. That means we can pull this sine out. Okay, we can pull that sine out, and then so what are the simplifications we can do? And then you can combine that with the other sine term. So that means you finally get you have to add the two. So you simply end up getting negative 1/3 sine 2t plus 2/3 sine t. That's what you get. That's from that. And then what we can do is now we can write the complete expression xt. So xt is simply going to be L inverse of sx. So which is from these two you're going to get negative 1/3 sine 2t plus 2/3 sine t, and remember there was another term, that term gonna give you 2/3 sine t. That's the term we did not bring into the partial fraction, and you can see that these two get cancelled actually. So that means your final answer is negative 1/3 sine 2t. Actually, this solution suggests that if you had used the partial fraction, you might get the answer quickly for this particular problem. So it depends on the numbers that you have. Just to see that, let's see. So that means this suggests that there should be a special simplification for this problem. So let's see whether that's the case. So I'm going to show you this trick here. Okay, so there are certain things in mathematics that works very well. Okay, it's not always the case. So what we have is we had 2 s squared plus 1 and then s squared plus 4 minus 2/3 s squared plus 1. That's what we had. Now what we can do, so my goal is to create a squared plus 4 term in the numerator, because once you create that term and split, they might get cancelled. So that's the whole point. So that means how to create a s squared plus 4 term. So let's take the common denominator here. So once you take the common denominator, you're going to get 3 s squared plus 1 s squared plus 4. So in the numerator, you're going to get 6 minus 2 times s squared plus 4. So to get. So let's simplify the top. You take the common denominator. And then you simplify the top. So then you're going to get negative 2s squared, negative 2s squared, negative 2 over 3 s squared plus 1 s squared plus 4, and you can see that the numerator is simply negative 2 times s squared plus 1. Now so 3 s squared plus 1 s squared plus 4. So what happened? This term get cancelled. See? So that's the case. So that means you simply end up getting negative 2/3 1 over s squared plus 4. That means this simply suggests that the if you take the inverse of this, so you can put with the we can put the 2 with that. So this simply suggests that if you take the inverse of this whole expression, you should get negative 1/3 sine 2t. So this is just an algebraic trick that works very well. So what we did was just take the common denominator. Once you just take the common denominator, it simplifies very well. But that doesn't happen always. So this is like a special situation where it simplifies very well. Okay. So now what we can do as the last problem, we're gonna do a theoretical problem, and just for your future applications, not much for this class but for future applications. So we can do one last problem. This is a theoretical application, so let's do that. So the problem is this. So let's say I'm gonna write again solving ODEs. So that's what we're trying to do. So we're gonna use the Laplace transform. Use Laplace transforms to solve ODEs. That's what we're trying to do. So this is the problem we're doing. Let's say find the solution. Find the solution to this problem. Let's say x double prime plus omega naught squared x equal ft. So ft is just an input function with x0 equal 0 and x prime 0 equals 0 for any arbitrary function, function ft, for any arbitrary function ft. So ft is just given function. We don't know what the function looks like. What is the solution looks like? So the answer, let's say let xs and fs be the Laplace transform, transforms of xt and ft. Okay, let's assume those are two Laplace transform. So now again, so taking the Laplace transform, of the equation. So we have s squared xs, and then all the initial conditions are 0, so it's going to go away. So you simply get omega naught square, which is a constant, sx equal fs. So the situation is like this. So let's say you have a system, and then you're going to put an input function ft, and then you have tried to find what is the output function. The output function xt. So that's the question. So you have a system, you put input function, you are waiting for the output function. So on this side you can simplify this as squared plus omega naught squared sx, which is fs. Now you can simply solve for sx. Okay, so let's do that. So sx is fx divided by that. So let's write it. So that means sx is simply fs divided by s squared divided by s squared plus omega naught squared. And you can see that this is a product between the two Laplace transform. So that means when you want to find the inverse, we can use that idea now and write the solution as an integral. So since the L inverse of 1 over s squared plus omega naught squared is equals to 1 over omega naught, L inverse omega naught over s squared plus omega naught squared, and we know that this is simply a sine, so that means it's simply going to be 1 over omega naught sine omega naught t. So omega naught becomes the frequency now. And you can say since, and let's say, and also not in that, L inverse fs gs is simply f star g. By inverting we have xt is simply the convolution product, is simply what we have is so it's simply going to be the convolution product of the two functions, right? So we can write this as like that, simply so in this case small f times 1 over omega naught sine omega naught t. So by the definition this is simply 0 to t. I'm going to say f tau, we leave it like that. So we say sine, so we're going to put omega naught, so we're going to replace t by tau over omega naught t tau, or you can switch the other way. So that means this is going to be the solution. So that means this is simply 1 over omega naught 0 to t f tau sine omega naught t minus tau d tau. So that's the solution. Okay, so that's the general solution for this problem. Now what we can do is we can see what will happen if you kind of have a special situation. So let's say this one. So let's say if this is special situation, if the input function ft is a harmonic motion cosine omega naught t. So that means, so what we are expecting here, so that means so for example we have a system, we're going to put like a function like that, so that's the ft function. So we see what is the solution look like. So that's the case. So for example, let's say you have a spring and a mass system with the frictionless, so there's no friction uh, surface. And then what is the solution look like? So that's how we're looking at. So that means you're gonna graph the solution curve, and you can see that after we do that, you probably end up with a like a function like that. So that's the solution. Okay, so let's see how it works. But this is the kind of situation. So you put a input function for this spring mass system, and you are waiting for the output. So let's say actually this is the input, and we are waiting for the output. So let's finish the rest of the calculation. And then you can see that in this case we can plug in that. So we already have the solution, we just need to plug in it and simplify it. So your xt is simply the integral from 0 to t. So what we have is, I mean, you can use any version here. You can even put the t minus 2 the other one, so it doesn't really matter. So since we have one of the problems solved earlier with sine cosine, so I'm going to go with the other version. So because you can always switch the two. So it is sine omega naught tau over omega naught. We're gonna put the t minus tau to the other one. So let's say omega naught, because we have already solved that. That's why it is t minus tau d tau, and so we can pull the omega naught out. So 1 over omega naught. So we have 0 to t. We have sine omega naught tau cosine omega naught. We have t minus tau d tau. So what we normally do is we're gonna pick this function as a and this whole function as b and use the trigonometric identity. And we did the exact same problem in few minutes ago. So doing that, so you end up getting omega naught. So what was our solution? Our solution was 1/2 t sine omega naught t. So that was the solution that we obtained earlier. Okay, so this is from previous result. So that means this is simply you can pull the 2 omega naught like that. So what we have is times t sine omega naught t. What is this solution? What this solution means, you can see when t goes on, you can see the amplitude of this function grows. Okay, so if you look at the graph of this function, this is how it looks like. So what's going to happen, so you can see it is a sine graph in between the t and minus t. So what we have these asymptotes actually. So so we have these two lines, one is a t, one is a minus t. So this is the t, this is the minus t. So what happened, you can see the sine curve passes through between those two curves. So what will happen is, it's just a sine, so it's gonna sine go between like that. So you can see that its amplitude grows every time. So that's the kind of situation. So so it's gonna fluctuate between t and minus t, because that's the amplitude part, and the actual curve is sine omega t. So the omega t gonna go between those two curves, and you can see the amplitude grows. So what we normally call, these are like explodes or breakup solutions. These are normally called breakup solutions. Okay, breakup solutions or blow up solutions. Okay, so in this case, normally what will happen, explode. Okay, the system gonna explode. So let's write that in word. So xt uh, grows without bounds. Xt grows without bounds. Without bounds as t gets larger. Uh, okay. So that's what happened. So it's gonna go like larger and larger and larger. Um, Good. So that's the end of the convolution method technique.